Did you see that? Oh, sorry. Let me just get everything ready to go here. Sorry. All right. So we're talking about trajectories. Now, if you're an MLG from the 80s like me, you don't need equations to do trajectories, right? We have trajectories in our head from playing so much scorched earth and artillery. But just in case you aren't an MLG from the 80s, let's look at the math. So we're talking about trajectories. And we've already been doing them. We've done drop and shoot, but now we want to do the famous arc, right? We know a trajectory is the path an object takes through space. And here in intro physics, we always talk about the special case near the surface of the Earth. Same as what we just did with drop and shoot, but now we're going to let it go up in the air and see what happens. So let's draw a trajectory as you've seen them probably before. If we have x here and y here, and we have a mass, and we give it an initial velocity up like that, then the trajectory it's going to take is going to be kind of like this, up and then back down. All right? And there's a few parameters of trajectories we like to calculate. One is how high did it go? We could call that little h. That's the height, obviously. We could ask about, we would call the hang time, right? How long was it in the air? TH for the hang time. Of course, this is space, but that's the time it was flying through the air. And we could also calculate the range. That's maybe the most important, is R. How far did it go? Where did it land? When you're trying to hit your opponent and you're playing artillery, R is most important. So we're going to calculate these from just our standard kinematics equations. We could really be bold and start like this. You know, we always break things into x and y. I just want to remind you that you can also write it even more general, just as the r vector. And the r vector follows the standard kinematics equations. The initial position is a vector that is just 0, plus v initial t, that has both components in it, where this is v initial, plus 1/2 g vector t squared. You can write it that way. And I'll point that out because in case you're ever doing something where you need to write it this way, you might wonder why I put a plus there when gravity is down, and it kind of depends on how you define gravity. So here I would write it this way if I'm to define gravity as g is negative 9.8 meters per squared I hat. So the negative can be in the definition of the vector when you're writing things kind of general like that. More likely you would want to write it like this. You would want to say r is, and let's solve the x motion. So in this case, there is an initial horizontal velocity, and the two things that you need to know going into a trajectory are the magnitude and angle of the initial velocity. You need the full vector. So you've got the theta, the angle, and the initial velocity that you shoot with. That's the initial thing in the artillery game. So the initial x component is just the cosine, right? So it's going to be vi cosine theta t. There's no initial x position, and there's no x acceleration. So that's the entire I hat component. And then in y, starting at the origin, 0, it has an initial y velocity, which is vi sine theta t plus, and it has gravity, plus 1/2 gt squared. And the normal thing to do actually now is to change this positive to a negative, because we're now dealing with just the scalar value of g, 9.8 meters per second squared. So we would call this minus 1/2 gt squared, and that's the j hat component. So this is the position vector version of a trajectory, and now we're going to use it to derive the hang time, the range, and the height.